Welcome to Valles Caldera National Preserve. We're standing in an ancient but dormant volcano that erupted 1.25 million years ago. What's remaining is a majestic landscape with forested volcanic domes interspersed with vast high elevation grasslands. On your visit here, you can see wildlife such as prairie dogs, coyotes, sometimes even bears, and mountain lions, and the state's second largest elk herd. In this video, you will see some of the science that we are conducting to try to learn more about Valles Caldera through forest ecology, our fisheries and wildlife, as well as our archaeology. Valles Caldera is one of the most special places in New Mexico, and on your visit, I hope you fall in love with it too.
Hi, I'm Bob Parmenter, Chief of Science and Resources here at Valles Caldera National Preserve. In today's presentation, we're going to use 4 examples of science here at the Valles Caldera National Preserve for managing natural and cultural resources. The 4 examples are going to include a post-fire, wildfire, measurement of vegetation, a post-fire, post-flood in a stream, looking at fisheries, cultural resources, that is field houses and artifacts that are hundreds of years old. How are they affected by fire going through the forest? And then finally, combining all of these scientific studies into a strategy to avoid high severity fires in the future. One of the major resources we have here at Valles Caldera are forests. And of course, when you have forests, you have forest fires, often started by lightning, but sometimes by carelessness of humans. What we try to do with forest fires is either manage them so that they can burn in a low intensity fashion or put them out. We also have planned or prescribed fires that allow us to do low intensity burns through the understory of forests. So fire management is a big deal here at Valles Caldera. The study that you're about to see is from our botany crew that is measuring the response of forest floor vegetation and stand structure to a stand replacement fire that occurred in 2013 called the Thompson Ridge Fire. This fire, of course, burned through a lot of forests, killed a lot of trees, and several years later we can see that the vegetation in the understory is now coming back, not as a forest, but as a montane meadow, a mountain grassland meadow. So we're documenting how fast these vegetation communities recover from a stand replacement fire. Now, the Valles Caldera has a number of different habitats in the preserve, and this includes forested mountainsides and valleys covered with grass with clear running mountain streams. And the beauty of the Valles Caldera is that it has so many different habitat types. But the main thing is that forests are throughout the preserve, and when they catch fire, they really burn hot. And so here was the view in June of 2011 that shows the Las Conchas fire burning up our ridges, moving across the mesas and throughout the grasslands, and burning extremely hot as the fire moved across, burning a total of 156,000 acres. At the time, it was the largest fire in the history of New Mexico. That record, unfortunately, was broken the next year. But this was still a big fire, burned through the day and the nights. And in the end, we had many forest acres had been burned to the ground. Basically, all the trees were killed and a thick carpet of ash. So one of the things we wanted to do immediately was to understand how quickly the vegetation would recover from this fire. And for that, we have botanists as a field crew measuring the vegetation.
Hi, I'm Ben Stout. I'm the plant ecology crew leader here at Valles Caldera, and today we're measuring the recovery of vegetation post Thompson Ridge Fire 2013. These are our crew members, Kathy and Chris, and they're doing a line point intercept transect to measure vegetation.
We have laid out a 50-meter transect, and we are taking data at each half meter. And this is a vegetation stick that I use to measure, and each interval is 5 centimeters. And so you put it on your meter mark, and you measure each plant that touches the stick, and you list their genus and species. And so, Chris, are you ready? 30 centimeters, Thurber's fescue, Kentucky bluegrass, coarse woody debris, and glitter.
And with the data we collect out here in the field, from plant species to canopy cover to such things as soil depth, we can use this to enter into our database, which allows us to also compare it to previous data throughout the years. And with that, we're able to measure such things as population changes in plants, canopy coverage, and even outside of fire, biomass.
The diameter at breast height for this ponderosa pine is 82.2 centimeters.
The height for this ponderosa pine is 37.4 meters.
From the data that the plant crew collects, we can see the changes on the ground of the increase in grass and wildflowers following the fire. This transect was from a mixed conifer forest that had a stand replacement fire. All the trees were killed. But the year after that, you can see the grass is starting to come back in. 2 years later, it's turning into a pretty good carpet of grass. And a mere 3 years later, we have almost complete vegetation across the burned area. And when we use the data to actually look at the percent cover here for the vegetation, in 2011, 2012, it was pretty low because it had been burned off and killed. But by 2013, it was equaling the control sites. The control sites here are listed in green. The burn sites are in red. And you can see that after 2013 into 2014 and 2015, the burn site actually had more grass and wildflowers on it than the unburned site. And you can see this again in ponderosa pine forest, where the same pattern occurs. Within 5 years, we had 100% cover across the ground, which means that the entire landscape was covered with grasses and wildflowers. The fire had turned the forest into a grassland. So with the vegetation changes over this time period, we also had other changes going on. When the fire first came through, it burned over a lot of the forests so that the soils were exposed. And when we had the forest exposed like that, when thunderstorms came, it would wash the soil and the ash into the creeks. And then these things turned into massive floods. And you can see a photo here of a little tiny creek that suddenly has turned into this black raging torrent. And this creek here that was normally just a couple of feet wide is now 100 yards across, with just totally flooded with black ash-filled water. And the scene of just massive quantities of ash and tree trunks and branches floating down the stream really was a stark reminder of how devastating these floods can be. This picture shows the difference between stream water that was not in a flood on the left with a water sample from the flood. And obviously it's got a lot of ash and dirt floating in it. That type of water can kill fish. And indeed, we lost 35,000 trout in one afternoon on the preserve as a result of these floods. Not only was the water very bad for the fish in terms of chemicals, but it was also bad because it clogged up the gills of the fish. So what we wanted to do was be able to follow the recovery of the fish and to see how the different species of fish interacted. To do that, our wildlife and fisheries biologist, Mark Payton, was out on the preserve recently doing some fish sampling with an electroshocker.
After we identify each of the individual species, we're going to measure the lengths in millimeters, and then we're going to measure the weight, and then they go into a release bucket over here. In each of the capture buckets and the release bucket, we have aerators to keep the fish calm and to keep them breathing with fresh oxygen going into each of the buckets. And then our data sheet here will go through and tabulate how many of each of the species we get, along with how large each of the fish are. They each fill a different ecological niche, and this one actually will go through on the bottom of the streams, feed on everything that's fallen down to the bottom of the stream bed, and helps keep our systems clean. So these are really neat fish. The Rio Grande sucker and the Rio Grande chub are both endemic to this part of the United States, following the Rio Grande River Basin. This is the other at-risk native fish species we have here, following the Rio Grande River Basin. This one, don't know much about really. There's kind of a lack of research data on either of the Rio Grande chub or the Rio Grande sucker. Part of the data set that we're collecting here is long-term population dynamics for these species, and as they relate to the predators. And so the Rio Grande chub and the Rio Grande sucker populations seem to be doing really well here on the Valles Caldera, but other than the population dynamics, there's not much natural history information really known about them. So we'd usually use some additional work on both of those species. After we've captured and processed each of the fish, we go ahead and release them back into the stream. We're going to do that right now. Well, swimming off, all in good health.
So the data that Mark has collected from the streams on the Valles Caldera tell a very interesting story. We've been sampling brown trout since 2003 for the last 17 years, every spring and fall. And you can see on the left side here, the number of fish per 100 meters of stream. We sample this in the same place every year. So as those years go by, you can see the population, it bounces around a little bit, but it's relatively stable. But when you hit the fire in the spring of 2011, the fish population of brown trout just crashes. It goes extinct until just a few of them start coming back in and finally start building up the population in 2015, 16, and 17. And by 2017 and 18, we're back to normal again. However, in this next picture, we superimpose the other species of fish on the brown trout. The brown trout, again, same graph, it's the black line moving along here, and you see the population crash in the spring of 2011. The other fish are the prey species that the brown trout eats. So you can see over many years, the brown trout suppresses the populations until the brown trout is wiped out in 2011. And then suddenly, all the other species of fish start to become very abundant. There you can see the data on this slide, just huge numbers of other fish. But then, as the brown trout recovers in numbers, it starts eating the other fish, and the other fish are pushed down again. This is a classic example of what we call predator release. That is, the predator, the brown trout in this case, is removed from the ecosystem, and all the other species that the brown trout used to prey on now are become much more abundant. But then as the brown trout recovers, the other species are pushed back down again. Now, from these fish studies, we can move into cultural resources, because we know what is happening on the land and along the creeks. We now want to know how these sorts of effects impact our cultural resources. In this case, on the preserve, we're talking about ancient prehistoric field sites, such as field houses, as well as artifacts, pieces of obsidian that are made into tools and weapons, as well as pottery. So to do this, we have archaeologists with the preserve who work on these particular issues.
I'm Nick. I'm the archaeologist at the Valles Caldera National Preserve, and I'm coming to you from the Banco Bonito, which is in the southwest corner of the preserve. It's a little different than the rest of the preserve. It's this open ponderosa pine woodland, rolling hills, drier. 700 years ago to about 300 years ago, people lived out here and farmed in small fields. And during the summers, when they were growing corn and beans and squash in little alluvial fans around the Banco, they would live in what we call field houses, which are very small structures that are just shelter enough for one or two people. And that's what I'm standing in front of here. The walls of the structure are built of the local volcanic tuff, which is a compressed volcanic ash, and it's fairly soft rock. So if a fire comes through, as fires have for hundreds of years, a low-intensity fire that just burns up the pine needles and goes through isn't going to hurt this structure. But if we have a lot of fuel on the ground and we have logs up against these walls, then the rock can actually start to cook with the high heat and break apart and crumble into pebbles. And you know, if that happens a couple of times with high intensity fire, these walls will start to fade into the ground and we won't be able to see these structures anymore. Another thing that can happen is these structures, they tend to hold snow in the winter and they help collect rain in the summer. As a result, trees like this guy like growing right up against the wall. Now that's not too much of a problem while the tree is alive, but if the tree dies or if it catches on fire during a heavy fire, then as the tree burns, it burns down and down, and the roots themselves begin to burn. And as those roots burn, they heat up the rock around them, which starts to degrade that rock. And once it's finished burning, you have a hole in the ground where the stump used to be, and that can undermine the walls. So that's one way that fire can impact even a stone structure like this. So one of the resources that the Valles Caldera is best known for is obsidian. This comes from a couple of sources inside the caldera, and obsidian is a volcanic glass, and you can use this to make extremely sharp-edged tools. People have been coming out here for over 10,000 years to collect this resource, and it's been traded across wide swaths of the country. We find it as far east as Mississippi, as far north as North Dakota, down into Mexico. So it was a resource that a lot of people wanted to get their hands on.
So one of the problems with fires that burns over a site with obsidian points or tools is that it changes the water content in the actual obsidian piece. So that scrambles the timeline that scientists would normally use to date the age of the point.
I'm Stephanie Bergman, the Cultural Resources Program Manager at Valles Caldera National Preserve. We're currently at 8,500 feet. This is some evidence of the highest elevation agriculture found in North America. Ceramics can tell us a lot about when sites were occupied and who they were occupied by, because they have very stylistic designs, which we can associate with certain artists from different pueblos in northern New Mexico, such as this black on white stylistic pattern that is often associated with this region in the Jemez Mountains in the Pueblo of Jemez. So these ceramics have been made for over the past 700 years, and archaeologists determine it by the different dating methods that we use. One dating method is indirect or relative dating. Now, using this method, we can create these typologies of ceramics because we find a large enough sample from certain areas, and we can work with our tribal partners to kind of determine who was making this and when.
Just like obsidian, if a fire burns over a site with ceramics, it will damage the pieces to the point that it will be more difficult for scientists to date how old they are.
Really, all this research is telling us is that we need to bring fire back on this landscape. We just need to do it in the right conditions so that it doesn't damage archaeology sites. And one way that we also do that is working with our tribal partners. So right now we have people from the Pueblo of Jemez that will come out here and hand cut down some of these trees from their ancestral sites so that they don't come through and get destroyed in a fire.
So what we've seen here so far are examples of how we apply science and technology to forest vegetation, to fisheries and stream ecology, and cultural resources. Now, as we take all of this together, we could then say, how do we develop a management strategy to prevent these effects on our resources? Because we know that when fires come along, they're going to burn hot. So our forests today, many of our acres of forest look like this. These are dog hair thickets, where the trees are as thick as the hair on the back of a dog. And if a fire starts to come in here and really gets going, it will just burn this forest to the ground. So what we want to do is start to manage the forest by thinning the trees, getting a much lower density of trees. So we bring in heavy equipment like this feller buncher that cuts down the trees and strips them and gets them ready for market. This is what a forest would look like after it's been thinned. We don't cut all the trees. We just take out a bunch of them to open it up. Very park-like structure here. And then the logs that we want to ship to market, we stack on the side of the roads so that logging trucks can come along and pick them up and carry them down to the mill in Jemez Pueblo in our case. And there the wood is made into lumber, vigas for houses, chips, firewood, all kinds of useful products to help our local economy here. And then we'll have people come in to burn an understory fire, a nice cool fire that stays down in the grass and doesn't kill the remaining trees. But that burns off all the slash and the needles and whatnot that were created during the thinning process. Once we're all done, this video shows the difference between pre-thinning and post-thinning and burning. And you can see the radical reduction in the density of trees and the opening up of the forest into a very park-like environment. This is what forests look like in New Mexico before the late 1800s. So if we take the forest that we've thinned and burned and then let it grow for another 100, 150 years, it will turn out looking like this. This is an old growth forest on the preserve that will be the model for many of the forest restoration treatments we've undertaken here. And if we're good and lucky and manage the property very well, we'll be in great shape to have recreationists and visitors to the preserve for centuries to come. So this is how we apply science and technology to the land management on Valles Caldera National Preserve. Thank you very much.